Okay, let's finish this thing. I don't know what time you're watching it, but I'm recording it and it's happy hour, so let's get it done. Example 4 has a graph for Cyprian honeybees raised in an apiary. Okay. How does the rate of population increase change over time? When is it highest? When is it concave up? And when is it concave down? So you can see it starts out increasing at a decreasing rate, concave up. At about 12 weeks, it switches to increasing, actually more about 10 weeks, hard to tell. Starts increasing at a decreasing rate. So concave up, concave down. Where it is growing at the fastest rate is where it changes concavity. So right around 11, 12 weeks, let's see, 12 weeks. It appears to be concave up on 0 to 12 and concave down on 12 to 18. So, and it levels off at what is called the carrying capacity. So, we already talked about inflection points before we defined them. But an inflection point is where we change from concave up to concave down, which leads us to the second derivative test. If you have a critical value and the first derivative is equal to 0 and the second derivative is positive, then you have a local min. If the first derivative is equal to 0 and the second derivative is negative, then you have a local max. Okay, let's think about what it means. First derivative is equal to 0. Second derivative is positive, so you're concave up like a cup, you have a min. If you're concave down like a frown, you have a max. Let's look at this example. We decided we had a max at 4 and at 8 because our first derivative was equal to 0 at 4 and at 8. We change from positive to negative. So the first derivative test said, yes, indeedy, we've got a max here. Second derivative is negative. Second derivative is negative. First derivative was equal to 0 at 6. We changed from decreasing to increasing. So we're thinking we had a min, and the second derivative was positive because we were concave up like a cup. So our whole goal in this is to be able to sketch curves. We're not going to be able to sketch the really complicated ones yet. We need L'Hopital's rule, and we'll talk about end behavior. But we can do example 6, because it's not too hard to graph. So it is a 4th degree polynomial. Even without knowing calculus, we have a pretty good idea what it looks like. Positive leading coefficient, its ends go up. And we also know where it crosses the x-axis. So even before we start thinking about calculus, I can factor an x out, and I get x cubed. Actually, I factor an x cubed out, and I get x minus 4. So I know that it crosses the x-axis at 0, and it crosses the x-axis at ichi, ni, san, shi, 4. Okay. I know it crosses because I remember my pre-calculus that says if we have a odd multiplicity, we cross the axis. If we have an even multiplicity, we touch the axis. So I know it's going to cross at both of those places. Let's take the derivative now. So 4 falls down, 3 falls down, gets multiplied by 4. I'm going to set this equal to 0. And let's factor out 4x squared. I'm left with x minus 3, not 12. So this is equal to 0 when x is equal to 0, or when x is equal to 3. Let's look at the second derivative. I think I have room to do it right here. Second derivative is equal to 12x squared minus 24x. That's equal to 0. 12x times x minus 2. So at 0 and at 2. So I'm going to make myself a nice friendly sign chart. I need 0, I need 2, and I need 3. I'll make a row for the first derivative and a row for the second derivative. So the first derivative, if I plug in something less than 0, then the first derivative, let's just go ahead and plug it into the old table function. Put the first derivative in, it's 4, clear out the old stuff, 4x to the third power minus 12x squared. We'll do some plugging and chugging. If I put something negative in there, something like -1, I get a negative thing out. Now it's not going to change sign again until it gets to 3, so I can plug in anything between 0 and 3, and it's going to be negative. And then if I put in something bigger than 3, something like 4, I finally get a positive thing out. So it's decreasing, 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 finally it starts increasing. Let's look at the second derivative. Second derivative changes sign at 0 and at 2. So actually I don't even need my calculator for this one. Happy parabola changes sign at 0 and 2. So plus, minus, plus, plus. There we go, because it changes at 0 and 2. So we are decreasing, concave up, decreasing, concave down, decreasing, concave up, increasing, concave up. Now, if I want to get a pretty good idea of what this looks like, I want to plot some points. So we have an inflection point at 0. We have an inflection point at 2. And at 3, we change from decreasing to increasing. So we have a local min. I do know where it crosses the x-axis here at 0 and at 4. So let's see what the function value is at these other important points here. So I'm going to go back and switch out my function and put in, instead of the derivative, the x to the fourth power minus 4x to the third power. Now I'll put it right side up for you. So let's see what my function value is. We know what it is at 0. Let's see what it is at 2. It's negative 16. So negative 16. And at 3, it's negative 27. I didn't give myself nearly enough room. It's negative 27. So, as usual, my picture is not to scale. But I know I have an inflection point right here. It's decreasing concave up until it gets to 0. So decreasing concave up. Then we're going to have a little flat spot. I knew it was going to flatten out because my derivative is equal to 0 at 0. So it flattens out and switches from concave up to concave down. It stays concave down until it gets to 2. Then it switches back to concave up. It reaches its minimum, its local min there at 3, and then it stays concave up forever. Now let's see how closely my picture resembles the pretty picture. I think that is pretty darn good considering my art skills. So, what does the second derivative say about the function? It's inconclusive if the second derivative is equal to 0. There could be a max when a second derivative is equal to 0. It also fails if the second derivative does not exist.